So despite some submitted issues that we experienced again, our TAs and mentors did an excellent job, and we will definitely get the grades over the weekend. So much earlier than on exam one. And of course, we didn't quite make our plan to release, to get you the grades back in 1 week, but we got much closer to that goal than on exam one. So hopefully that's a good sign. And yeah, let me check if our panelists are all here. Can you folks please identify yourself? Those who received an email from Cheyenne saying that you are panelists on the 1st of October. Okay, Frieza, got it. Aria, got it. And three more people. Matthew, and I think we have Jink and Uday. And let's start, and let me start sharing something so that you are not bored. Beautiful day, and I know it's Friday, so it's probably very hard to stay focused on the comp.org material, but hopefully you can have some fun over the weekend. I know you had a Fox exam a few days ago, so hopefully that is behind, and you can enjoy beautiful weather. And yeah, while it is still warm before long and cold Troy winter arrives. All right. Well, we have an exam next week, right? So, but hopefully that is, not as cruel or as daunting as Fox homework. And we heard everything students had to say about the preparation for exams. So I already have my practice problems for the exam, and I just shared that with our TAs and mentors so that they can, look at it and suggest maybe a few other things need to be added or a few problems, need to be changed. So they will review those practice problems today, and I plan to post them at the end of the day today. So please don't make us write MIPS. Sorry, folks, that's probably not what I can do. So expect to write MIPS. That's pretty much inevitable. Otherwise, how do we check your understanding of MIPS? And I know homework is going to be there. So homework 3 is going to be posted over the weekend. But this class is so heavy in MIPS. It's unavoidable. Um, there's no way we can avoid writing MIPS on exams. The good news is you can use reference materials. Okay, so you can, you don't have to memorize even like all the instructions, right? You can just use that reference card that I mentioned, and that is in your textbook. If you have a physical textbook, and I posted it under course materials. So that means that you have that reference for all instructions, and okay, so there's a request to post homework assignments earlier. I will certainly try to do that. I cannot promise it for this homework because Friday is today, but I will definitely try to get them, you know, out to you earlier than over the weekend. But probably this time it's going to be over the weekend. Okay. I will try my best. Okay, and yeah, I can handle MIPS, but no Linux. So yeah, there will be no question specific or targeting Linux anymore. But MIPS, sorry folks, pretty unavoidable. I hope you understand. Can we get more basic exercises on MIPS? Sure. So there are examples in lecture notes, and hopefully we go over more examples in slides today. Okay, and Jin Kun is here. So our other panelist for today. So we will, yeah. So I marked that. So I think we are only missing Uday. But if they show up, just let me know. Okay. Can we also get Lab 3 solutions earlier? I'll try my best, but several people had excused absences, and because of that, they received a permission to submit their Lab 3 later. And until those people are done, I cannot release solutions for obvious reasons, right? Because then those people would have those solutions for free. So as soon as my TAs report that they are done with all people who had excused absences on Lab 3, I will release the solutions immediately. I have them already written. They are ready to be released as soon as everyone else is done. Okay. All right, and so what else? Oh, submini polls from last time. So we only had 2 of them, but let's go over them and let me start sharing. Finally, start sharing something. I think I already said it, but didn't actually share anything. All right, so yeah, this is actually one of the reference sheets. And remember, you can use as many as many non-electronic reference materials as you want on the test. So just try to think ahead of time what could be, what would be something that you might need on the test. Okay, and so let me. Yeah, and this is the reference card that I posted in the course materials. And here are our lecture polls. Yeah, I don't think we will have a chance to go through all 7 lecture 9 today's lecture submini polls today, but maybe 6 is that would be good. So and our lecture polls from last time. So here they are. So that was this. Oh, and let me pull up my chat and Q&A. And it drives me nuts. I have to stretch my windows for Q&A and chat every time I switch the mode in WebEx. It just doesn't remember my previous settings. It's very annoying. But anyway, and all right. So here we are, and the answer is all the options are correct. And the answer was actually on one of the slides. So hopefully that wasn't hard. So all of those components might potentially affect the CPI, because what is a CPI? It depends on the blend of the instructions in a particular program, right? If you have a compiler generating more division instructions than some other compiler for the same program, and division instructions have a higher CPI, right? More clocks per instruction. Of course, the more division instructions you have in that code, the greater the average CPI of a program is going to be, just because of their contents, just because of the distribution of different types of instructions. If you're emitting the code that is heavier on longer instructions with higher CPI, of course, that drives your overall CPI for the program as a whole up. And of course, instruction set architecture determines the CPI. Clearly, we can design a different processor with a different ISA, and it would have a different CPI. Programming language, similarly. So some programming languages, are like lower level, and they would have tend to have more instructions, but instructions would be shorter, or statements would be shorter when they are translated into their machine code. So there would be like a closer correspondence between their statements from their programming language and the instructions in their compiled code. And algorithm, of course, determines the CPI. You can come up with an algorithm that uses a lot of division, or maybe you can go with a different algorithm that that is not using division at all, and of course that would affect the CPI. Is there a formula sheet for the written homework questions? That's a good question for the Q&A. And I see that we don't have a lot of questions in the Q&A right now, so probably our panelists are bored. Remember that for panelists to earn their quarter of a point per lecture, they need to answer at least at least one question each. So please feed questions to our Q&A, and if panelists see that they're unable to answer any particular question, just serve that question to me. Just unmute yourself, one of the panelists, and let me know that, hey, there's a question that that only instructor it appears only instructor is able to answer. Okay. So, all right. Yeah, be generous. Let them earn their points, okay? Because they're not getting them for free. They earn them for the great work that they're doing and helping to run this class. So let's be appreciative of that. Okay, so that was poll number 1 from last time, and poll number 2 was this one, and so here I agree with their majority of vote, and you could apply their formula, and all the formulas are in the slides. All the formulas are in the textbook and in the Zybooks, and I will point out those formulas again in a few minutes. But to finish off with this poll number 2 from last time, what would be the easiest way to compute it? Remember, you can apply all the formulas and get the correct answer that way. But even intuitively, look at the problem. It basically says that there are 2 parameters that we are changing, right? So it's like 2 knobs that you're turning. And one knob says that the new compiler will generate fewer instructions. So it's good. So, in that sense, so we put this factor that 0.8 that determines that it's going it's going to get better. But unfortunately, there is another factor, another knob that we are turning in the opposite direction that says that the CPI will increase by 20%, which means 20% more means 1.2. So we multiplied by 1.2, and why this calculator does that, but it is supposed to be this. So if we consider both factors, overall, it's going to be the improvement of 0.96. Okay, so that's that's the factor that you need to multiply your 15 seconds by, and you get 14.4. So the program will run faster, so it's an improvement overall, but not by much, because there are 2 factors that almost balance each other out. One helps us increase the performance, another one hurts the performance. Okay, is that making sense? All right, and so on to couple of things that I wanted to mention with respect to MIPS and other miscellaneous things. So one, if you go under, no, not here, not introduction to C, but to week number 4, introduction, and the same material, of course, is in the textbook as well. And there is this table here that I want to draw your attention to. Are we now 100% done with C after the exam? We are done with C, but C will be with us for the entire semester, because you will be writing all different kinds of stuff in C. So eventually you will be asked to write a compiler for MIPS in C. Okay, so we assume that you mastered C, and now we can just use it as a tool. So it's it's not going to be specifically on any exam. And none of the exams will target specifically C, but you will use C as the tool for other different stuff. Okay. Well, yeah. If you didn't master C, at least hopefully you are comfortable with C. Sorry, I didn't mean to upset you folks, but no, we won't ask you to write a compiler for MIPS in on the exam. It's more like the homework problem. But we may ask you to write a compiler for one instruction, not for the entire MIPS, but for a subset. Okay. All right. So back to this table. It's the official terminology that I will be sticking to, and it has been around for a while, but still many people do not, even people who are in computer science, especially people who are in computer science for a long time, because, when I was growing up, it was before this standard was actually adopted. So, to me, it looks like a little foreign, right? A little weird, but hopefully for you folks, this kind of terminology is more natural. So, many years ago, many decades ago, the CS people, computer scientists, computer engineers were not making this distinction what a kilobyte means, and that was causing some issues because computer scientists, computer engineers would treat kilo as 1024 as 2 to the 10th, whereas the rest of this, all the other sciences, physics, and all other natural sciences would follow the traditional definition of kilo being exactly 10 to the third, 1000. Okay, and the same for all the other prefixes, mega, giga, tera, and so forth. And for the longest time, it was considered like, oh, you should be able to figure out what kilo means from the context. So if you're reading a computer science paper and you see, this KB, you assume that that K means 1024, 2 to the 10th. And that's how it worked. But it was still confusing because, many people, for many people, it wasn't clear from the context what K exactly means. Does it mean 10 to the third or does it mean 2 to the 10th, 1024? And that's why they came up with this, official standard where kilo is reserved for exactly 1000 or 10 to the third as it has been for years before computer science, computer engineering came into existence, and computer science, computer engineering folks are given a separate prefix, which is kind of derived from kilo, but has this by in it. So by means for by stands for binary. So instead of kilobyte, we now have to say kibibyte, right? Where ki is the first from kilo, and bi means binary. So if we want to say kilobyte, meaning that it's 1024 2 to the 10th bytes, we have to say kibibyte. And the abbreviation is not KB, but KIB. And so in English, it's K is traditionally written as a cap, so it's capital K followed by lowercase I and then capital B. That capital B is important because if you put the lowercase b, it actually stands for bits, and it is something that exists. So if you look at any kind of lower level stuff or transmission speeds or anything like that, they are often measured in bits instead of bytes. So if like kilobits or kibibits per second. So for bits, you would use a lowercase b, and it would mean, so if I have capital K and then lowercase ib, it means a kibibit. And if I have it written like that, K capital I lowercase b capital, it means kibibyte. Yeah, kibibyte is really cute. And I don't think it's the cutest. My personal favorite is Yobibyte. How about that? I love it. Just the way it sounds. All right. So that's the thing. So don't be confused when you see in this book, our textbook. Of course, it follows the standard. So you will see that those KIB, MIB, or well, MIB abbreviation is cool, right? MIB. But in our context, it would just mean maybe byte. And so hopefully you are expected to be reading the textbook. Yes, absolutely. I don't think you can, unless you have tons of prior experience, I don't think you can do well in this class if you do not read your textbook. That's why it is a mandatory textbook for this class. So whether you get Zybooks or a paper book or an electronic book, it doesn't matter. But yeah, you are expected to read the textbook. Okay. All right. And to be clear, both values, both decimal and binary prefixes are used, and of course, to make just everything more confusing. So if you let's say look at the capacity of your hard drive, it is going to be given in um, gigabytes or terabytes. So storage manufacturers traditionally stick to the 10 to the 10 to the power of whatever um, concept, right? 10 to the third, 10 to the sixth, and so forth. So if your hard drive is 1 terabyte, it's exactly 1,000 to the fourth bytes. So it's actually less, right, bytes than if they were using tebibytes. And the rumor or the speculation was that it was done on purpose so that many years ago, so that you buy a 1 terabyte hard drive, and it actually contains fewer bytes than in a binary tebibyte. All right, so it just you can sell the same stuff for more. Okay, and yeah, for Zybooks, there are so I put some due dates for practice problems just to help people stay on track. But it's you can still submit outside of those due dates. Okay, so we still haven't figured out a way to encourage people to do those practice problems and labs and whatnot. So I was asking before, but that lecture, my WebEx crashed before I could save chat. And guess what? This, beautiful, sophisticated Cisco software, it's if you didn't save your chat before the lecture ended, before the meeting ended, that chat is gone. So there's no way to save it. So I was told that it is part of the recording, but I couldn't figure out where actually it is. So, from that lecture, the chat that we had about what would be a good reward for people who are doing Zybooks exercises, and maybe we can come up with something similar for people who are not using Zybooks, like give some recognition for people uh, who are doing exercises at the end of the chapters. So I'm still open to suggestions. I'm still willing to recognize those people. And yeah, please write your ideas in the chat. Again, sorry about that, but like I said, my WebEx, that lecture, I think it was 2 lectures ago, just crashed before I could save anything. Amazingly, WebEx does save Q&A automatically. It doesn't save the chat, and there's no way you can configure it to save the chat automatically. If you have the real textbook, how do we know what pages, chapters to read and when? So that you can track by the slides. So I usually put the slides that we cover in the lecture, and of course the chapter as well. But it's actually a good suggestion. So if you folks want me to, I can actually mention in their notes, in my lecture notes, what which pages or which chapters and section I would like you to read before the next lecture. So that I can certainly do. You think it would be helpful to those of you who are using the paper textbook? Okay, yeah, all right, done, sold. I will start doing that from. Yeah, I will actually update our slides today with the material that we will be covering on Tuesday. All right, so that's about that weird. Well, it's standard. I shouldn't be saying weird. It just to me it still sounds a little boring. There's terminology with kibibytes and mebibytes and gigabytes and so forth. All right, so that was one thing that I wanted to mention, and then for the formulas, if you just go to performance section, you will see the formulas that are also in the slides. Like here, that was our first formula when we were discussing, what would we choose as the performance metric, and we were saying that, well, performance should be something that follows the idea that the higher the better, not lower the better, and that's why like the execution time itself is not a good performance metric, because of course it's the lower, the shorter the time the better. So we decided to invert our execution time and use that quantity as the performance metric, and then there is and the next block of formulas here. So when we were discussing the execution of the time as a function of their total clock cycles for a program, and of course their cycle time, which is the inverse of their frequency. So that was that formula, and here's that example that we also went over. And finally, when we introduce the average clock cycle per instruction, the average CPI, that's another formula. And finally, we had this formula when we have instruction count, CPI, and clock cycle, and we can have different classes of instructions. So not all instructions necessarily have to have the same CPI. So we may have a blend of instructions, and in any program, that blend would be potentially different. That's why we have to do this weighted sum. So that's the final formula. Okay. Are we good with that? And so next thing that I wanted to talk about, let me. All right, homework 3 I mentioned. Homework 2, yes, it was due last night. Hopefully it was okay. I think their average on auto-graded submissions for C code was like 89. So, and a lot of people got, most of the people got 40 out of 40. So I think it went pretty good. I had a few questions in my mail last night that I didn't have a chance to go over, and just in general, your chances of getting a response to your question are higher if you post it on the Submini forum, because more people will see it. But I will get, and of course you can write to me, and I will make every effort to answer promptly. But it may not be within a few hours. So I'm hoping to handle all those emails about homework 2 problems from students that I received last night. I'm hoping to get through them today or tonight. And hopefully, yeah. So if people need to use extra days on homework 2, of course they can. So you can use, remember, up to 2 late days, provided that you have enough late days. And late days, everyone starts with 3, and then you can earn late days by answering Submini polls. And I'm actually looking at their parameters of our Submini polls and lay days, and I'm not particularly happy at the rate at which people earn their lay days, because I think we give 1 lay day for the first 15 points, but then we give an extra lay day for 30 points, which I think is a lot. So I'm thinking about making making it so that students can earn their late days at a faster pace by saying that let's do extra late day for every 15 points instead of 30. Yeah, that's what I'm thinking. You like that? Okay, cool. So let's do that on Submini. That requires actually changing Rainbow Grades source code. But I should be able to do that. And hopefully I don't mess it up. But please, check your extra late days to make sure that they are what you think they should be. Okay, cool. I will do this over the weekend. So probably not tonight, but over the weekend that change should be made. Okay, and we are back to. Okay, we are back to our material. Okay, so let's let's go over stuff that we were kind of skipping earlier to get faster to the MIPS material, and then so that we can be done with at least chapter 1, and there in chapter 2 the pieces that we kind of skipped over. All right. So first, the history stuff. I'm still not gonna spend too much time on it. All right. So please read the textbook. I think it's pretty interesting stuff. It's I don't think we will be expecting you to know like every single date and every single name that comes up here on like exam or something. There's usually more important stuff that we really want to test you on. But let's just let's just agree that please read this in your textbook. So what it basically talks about is their history of computing and the revolution that that computers actually introduced into our world since first electronic computers came into existence in late 1940s, and all the progress that is associated with the computers that would not be possible without computers. And many things that we use like cell phones and engines that are controlled by computers and World Wide Web and search engines and all that stuff that would not be possible without computers. So computers are everywhere, but there are different types of computers. So there are personal computers like your laptops and desktops that I'm sure you're familiar. There are also server computers that usually you don't have a direct access to. So usually you access them through the network, and then in many cases you just have a command line SSH terminal access to the computer. And a good example would be Submiti. Submiti does have a UI which all of you work with, a web UI, a web site that is a front end for Submiti, but Submiti also has a backdoor for advanced users or power users, where instructors and head TAs are able to directly connect to Submiti and do some advanced stuff through the command line, and that's a very typical scenario for servers, or at least for administering, managing, or doing some advanced work on the servers. And then there are supercomputers, so large machines that are that are only available through some kind of terminal or through a landing pad. So you never work at the supercomputers directly unless you are an admin in their supercomputing center. And as you probably know, RPI has a supercomputer. It's actually in the list of 500 most powerful computers in the world. And if you take a parallel computing course with Professor Carruthers, you will actually have a chance to work on the supercomputer as as part of that class. So for that class, you have several assignments that you do on a supercomputer, because it's not a coincidence. Professor Carruthers is the head of the supercomputing center at RPI. So that class is privileged to allow students to actually work on that supercomputer. And it's very cool. I took that class myself when I was a grad student, and it was fantastic. And it's a 4,000. It has a 4,000 level version at least, so any undergrad can take it. And if you're a CS major, that class would count towards your capstone or your CS option. All right. So next class of computers, embedded computers. So those are usually small, very not so much powerful computers, but that are ubiquitous, that exist everywhere in your in your electric kettle, most likely, in your car, probably hundreds of such embedded computers in your in your dryer, in your washer, and pretty much any equipment that has some, electric components. Even, something simple as, just an electric motor would typically have a control circuit that controls that motor, and that would be actually an embedded computer. All right, so there are many of them, and this is just we are in the post PC era, which means that PCs are not really the majority of computers. The majority are, I would say, embedded computers, and smartphones. You see that plot. It's pretty convincing. All right, so we have those personal mobile devices, PMDs, that are handheld, that basically you carry with you all the time. Probably, try to recall last time you left your home without without your smartphone, or some kind of replacement, or smartwatch, or something like that. All right, probably doesn't happen that often. Most people, you know they actually came to depend on those wearable computing devices that they wear with them all the time. And cloud computing, so that's another trend that is not new, but that came into more that became more popular in the last decade or so. So the idea is that we have some very powerful hardware that is accessible to users through the network, and that hardware is a lot more powerful than any of us would probably be able, or be would probably be able to afford to buy, and that hardware is shared between multiple users. So that gave rise to a bunch of different technologies like software as a service, and stuff like that. So we're not going to go into this area of computing in this class, but there is a class on distributed computing at RPI at CS. So if you think you like this topic, consider taking that class, distributed computing. It's also, if you're a CS major, it is also counted as your CS option and your capstone. Yeah, Microsoft has become a real big player in the cloud computing. So if you think back, 20 years ago, Microsoft was Windows and Office by and large. All right, those were their two products that were giving Microsoft the bulk of its revenue. These days, it's no longer true. Currently, Microsoft is making most of its money from cloud computing, and Microsoft has been pretty successful in this, right? So it is, on the market. I believe Microsoft is doing pretty well. Um, as compared to some other, big names in computing that are still around but are not doing so well. And if you think about market capitalization of, let's say, IBM, it is pretty much not going anywhere for the last decade or so, despite of all the efforts. So, of course, IBM is still alive. It's still, a huge name, but it is still trying to find its position in the modern world, right? So from IBM being their name in personal computers, and before that IBM being the number one name in servers, IBM then tried to kind of rebrand itself into IBM is a software company, and now they're still trying. I think they're still trying to find their their place in the current computing landscape. All right, so and yeah, that's basically the outline of what we will be covering in this class. So hardware software interface. So we're going much deeper than what you had previously done in other classes, like where you write your source code, you compile it, and you never really look into how it works. At the levels lower than than your source code, or the operating system. So we're gonna delve into that a lot in this class. And of course, it's going to be a lot about performance. And we have different components that affect the performance: the algorithm, the language, the compiler, the processor, the memory system, both in terms of organization and their amount of memory, and of course their I/O system, which includes your operating system. So these are seven great fundamental ideas that we will often refer to when we discuss different parts of their MIPS architecture, and other topics that we will go over, right? So abstraction, that allows us to simplify design and capture the general case, abstract from particular details of a particular problem and try to generalize and come up with a more general solution. Make the common case fast, and then parallelism, pipelining, and prediction. Those are advanced topics that we will touch upon in the second half of the course. And then, of course, their hierarchy of memories, cache, and different levels of cache: L1, L2, L3, and all that. We are going to spend a good deal of time in this course, and it's going to be tough material. So I'm not trying to to scare you, but it's going to be pipelining and hierarchy of memories. Those are probably two two harder topics in this course. All right, and so then in general, this is the diagram that shows where we stand with this course. So we're not going to go very deep into the hardware, because that would be the subject that would belong to computer engineering more than to computer science. And I know some students already think that this course is too much computer engineering than computer sciencey, but we need to kind of pry into the computer engineering stuff of things to have a better understanding of how our computer science stuff works, how our software actually works. So we will look a little into hardware, but mostly we stay here with the lower level software, which is called system software here, and this is one level below where you have previously been with application software. All right, and so what happens with your high-level language program when you compile it? So when you compile it, it is turned into their binary machine dependable code. So it's the code that it targets a particular hardware architecture, and this diagram shows that. And this machine code would be different for different architectures. If you compile your code, your C code into MIPS, it will the compiler would spit out their MIPS code. If you compile it for the x86 platform, that would be the x86 instructions, x86 assembly language. And then those mnemonics that we have seen already, those short commands like add, LW, and so forth, with all the arguments, they are trivially converted to the binary code, to numbers, and it's a one-to-one correspondence. So if you know that your commands are 32 bits, then you can take your command, this multiply with an immediate mul-y with those arguments, and translate it into 32 bits, into zeros and ones, so that you end up with 32 bits that represent this instruction. And you can go there in the opposite direction as well. So if I tell you, please, given that 32-bit binary number, give me the command, give me the instruction in MIPS that corresponds to that binary code, you would be able to do that. So it's one-to-one in both directions. And if you think about their high-level language and assembly language, there's no one-to-one, right? So in many cases, you wouldn't be able to reproduce the exact high-level language construct from the assembly language, because there might be multiple ways to do that. Okay, so that's that. And then this binary code is actually what is fed into the actual processor, and the processor executes those instructions one by one, and that's how your program actually works. And we will look into this. How does the actual processor reads just those zeros and ones and then understands what to do: add, subtract, multiply, move to memory, from memory, and so forth. And it's not a trivial question. It's actually a very hard engineering problem, but we stand on the shoulders of the giants. So it has already been done before us. So we can just look at the results and stand in awe. Thinking how thinking about their genius who actually came up with this idea. And it's not, of course, a single person. It's it's a number of different folks. All right, so components of a computer, there are four major components. Their control, their data path, the input and output. So input and output are pretty self-explanatory. They make sure that the system, the computer, can interact with their with the outer world. And control and data path are two pieces that comprise the processor. Control is what actually decides what their processor is going to do. It's the control that deciphers, decodes their binary commands, those zeros and ones that are fed into the control into the processor from their memory, from their input, and decides what actions, what tasks need to be performed. And data path corresponds to how data moves through the processor. We will see that the processors have a pretty complicated internal structure, internal organization, and data moves through different pieces of the processor at using a certain using a certain procedure, using a certain workflow. And we will talk about this data path, and it will get a little complicated when we talk about pipelining and pipeline data path, but we will go through this together. So don't get, again, please, I'm giving you some heads up, but don't get scared yet, please. Okay. And yeah, touchscreen devices is one of the examples of post-PC devices. Not really much to say about here. To say about those devices here. Yeah, so LCD screen. I'm sure you are familiar with those. All right. So we have a concept of a pixel, and traditionally it goes back to cathode. So CRT is a cathode ray tube display. So that's the technology that existed for for decades, but is pretty much extinct these days. But coming from that CRT technology, it is quite common in computer science and computer graphics to treat their upper left-hand corner of the frame as their pixel with coordinates 0, 0. So basically, you have a two-dimensional space, and each point in that space is a pixel. A pixel picture element is something that is the minimal, the atomic unit, the minimal unit that you can control their color of, and set the color of that pixel. All right. And then there's a frame buffer behind that, so that's just extra memory that allows you to interact with their display in a more efficient manner. And yeah, if you want to open your, so I believe this is iPhone 10, if I'm not mistaken. So if you have an iPhone 10 and you're willing to sacrifice it and take it apart and open the box, that's pretty much what you would see. A12, and you see this Apple here. So A12 is the YouTubers do whenever a new phone comes out, exactly. So you don't have to do it yourself. Yeah, unless you have you just have an extra iPhone 10 that you don't, or any other iPhone that you don't want. All right, so yeah, but this is pretty cool if you have an older device that you want to sacrifice and that you want to look at and open with your own hands and see what it looks like. Right, so a bunch of integrated circuits, as you can see, and this A12 is the main processor, the CPU. All right, so inside the processor, we have their CPU. So we already talked about it. It's one of their, so it contains data path and control. And data path and control are two of the four main components of any computer. And it also has external and internal memory. So internal memory, which we call cache memory, is usually on board on the processor, but not necessarily. It may vary. So it is possible to have cache memory that is actually a separate chip. And we will talk more about cache memory, what it is, and why we need it, and the whole memory hierarchy thing later on in this course. Okay, and so if you, this is something that would probably be a little harder to do than just opening your iPhone 10. But if you did open your iPhone 10 and you looked at A12 processor, and then if you somehow take the cover off A12, which you can't really do unless you use some kind of sandpaper or something like that, then you will see something like that. Okay, so that's the internal structure of their A12 processor, and you see that there are multiple cores. So there are small cores, and there is this memory system cache, and there is a GPU, the graphic processing unit core. So in the GPU, so that's that. Yeah, send down the cover. You can actually do that. I don't know if you know this historic thing that in Soviet Union was behind with a lot of development in electronics. So what they would do, they would buy an integrated circuit from the U.S., from a Western country, and there was embargo, so much of that was, of course, illegal. So there would be, spies, trying to get their hands on, the most recent ICs from the U.S., and they would bring that into the country, and then there would be, special institutes who would actually, take, kind of remove their processor layer by layer and study its internal structure so that they can then reproduce, make their own IC which with the exact same structure. So that was a big industry in Soviet Union, and that's um, that's how it was done. Yeah, so you can actually, if you're very careful and if you use proper equipment, you can actually send their this ceramic or plastic outer package, and then actually look at their, at the silicon, structure itself, and it has multiple layers, so it's not like all planar, right? So you have to, keep sanding layer by layer to study to see what's in the next layer. All right, so the big picture for abstractions we already mentioned, right? Abstractions allow us to deal with complexities, hide lower level details, and kind of generalize on different tasks and kind of see their commonalities, and then create their solution targeting that common case, targeting that the commonalities that we were able to observe, and that's an abstraction. All right, and instruction set architecture, that's their hardware-software interface. That's their, and they kind of go hand in hand. Their instructions that we have in a particular instruction set, they have to match the hardware. Of course, we have to make sure that instructions are, it is possible for the hardware to actually execute the instructions that we came up with. Okay, and of course we need storage. So traditional hard drives that are still around, despite the fact that in many applications they are replaced with solid state devices like flash memory, and there's also optical storage, your Blu-rays, and older technologies, DVDs and CD-ROM. And networks, of course, we need networks to make sure that our computers can talk to each other, right? So it's no longer the case that we have a personal computer that just stands on the table and that is not connected to the rest of their world, right? So it used to be the case many years ago, but of course networks make the power of computing a lot more because we can now combine compute power of different computers together, or we can simply share files through the network. And yeah, so here's your internet as one of the examples. Technology trends. So here we have an example of memory chips and how the capacity grew. So DRAM, RAM is our volatile memory, and we will talk more about different types of memory. So DRAM is one type of memory, and you see that starting from the first vacuum tube in 1951, and I think the first um, transistor technology for memory for storage was first in early or late 60s. And you see the relative performance per cost ratio, right? Yeah, to put things in perspective, I think like a memory device from 1957 that was able to store 1 byte of memory had a cost of close to $400,000, right? So one byte of storage, $400,000, and that was, of course, not adjusted for inflation. So it was there, 1957, $400,000, where you could probably buy a house for $4,000. All right, so that's amazing. The rate at which their technology was progressing for memory chips. So it's largely based with overall advancement of semiconductor technology. So the base material is silicon, it's semiconductor, and then of course when we want to build the actual circuits, we need other types of materials. So we need conductors. It's most commonly copper, sometimes gold. It's insulators. It's most commonly glass. Sometimes it can be some kind of plastic, and switches. So that's something that can be in either on and off. Typically, it's just a transistor. All right, and here's a pop quiz that just look at the numbers given and go with your best estimate for what a price of one gigabyte of RAM would be in 2005. So it's not that long ago, but it's not current. So you probably don't know that, uh, you know, uh, immediately because largely that was 15 years ago when I don't think many of you were interested in memory prices back then. All right, and if you're struggling, if you feel free to um, you know to Google it. All right, so like I said, it's more of a attendance thing, the pop quiz, than anything else, or a practice test. All right, so let me actually open that poll. So I believe it's this poll that I got open accidentally last lecture. Yeah, someone's saying they remember buying 16 gigs for $100 like 3 years ago. Well, I'm a little older than you folks, and when I was a kid, I remember my uh, friends, my older friends, buying uh, 4 megs of memory for $200. So 4 megs for $200, and that was like mid 90s, late 90s, right? So 4 megs, 4 megabytes of RAM for $200. So, and yeah. All right, so that's that, and then let's move on. And manufacturing ICs, I'm not gonna spend too much time. Please read it. It's fun stuff. It's not going to be on any exam, and so it's good to have a general understanding. I'm not gonna be spending too much time on this one, right? So the major takeaway here is probably that the larger the size of their wafer, the more defects we should be expecting, and the lower yield that there's going to be. So that kind of tells you why there are just natural limitations to the cost of an integrated circuit, which is determined by the manufacturing process. All right, so the performance stuff we already went through, and you had to practice with those questions on your homework. So hopefully that wasn't too bad, right? What was your impression on the textbook problems on homework 2? Okay, it took forever to type up. Okay, still doing them. Yeah, you can do that with. Not a fan of LaTeX, but hopefully the more you use LaTeX, the more you like it. It's amazing, all the different kind of stuff that you can do with it. And yeah, so if you're taking Fox, so those of you who are taking Fox, who's your professor? Who's your Fox professor? Just wondering. Malik. Okay, Professor Malik. So he wrote a book which I'm sure you know. Okay, that you use in class, and that book was written entirely in LaTeX. Can you imagine that? Like even all their pictures are done in LaTeX. So there's a library called TKIZ that allows you to do amazing things. Okay, so that is the amount of power you get if you use LaTeX. It's just amazing. So it has a steep learning curve. It can take some time, but it's it's really powerful. So I think as as a CS major, or in general as someone who's into computing, you need to know how to use LaTeX. And like I said, we are not insisting on LaTeX, right? So if you want your Word and your equation editor, go for it, and just save it as a PDF, right? But I highly recommend LaTeX. All right. So then the other consideration about integrated circuits and as it relates to our course to processors is that there are there is this problem of power, right? So the problem has several phases. One, of course, is the amount of power that is consumed by large supercomputers. If you look at the power consumption of some of the most powerful computers in the world, so their power consumption is actually close to power consumption of decent sized city, and their amount of money they pay monthly, like for RPI's computer, just for their electricity, is like several $1,000,000 monthly. So that's their monthly power bill. And the other side of it is, of course, even in your tablet or in your laptop, desktop, whatever, there is a problem of power consumption, because power is what? Power is heat. So if any device uses a lot of power, there's this problem with heat dissipation. And so that's why we need to kind of look into that a little. So this is the equation that tells you how their power is how is computed. So how to compute their the power that a particular integrated circuit is going to consume. And it has three components: frequency. Obviously, the higher the frequency, the higher the power. So if you if you are going to keep rising your gigahertz, it pushes the power up. A capacitive load is their overall capacitance, is their overall capacitance of their and of all their pins and all the internal components. And the reason capacitive load matters is it's actually related to frequency, right? Because the more capacity, the more capacitance is, the harder it is to keep charging and discharging that capacitive load, and that increases the power, because every time you charge a capacitor, every time you discharge a capacitor, there is a loss of power. So there you never get the same amount of energy from a capacitor that you pumped into it, right? You always get less because there are losses. So that's that. And a voltage, look, voltage squared. So it means the higher the voltage, the higher the power. That's why there is a trend, and it was very apparent in 20, 30, 10 years ago even, where integrated circuits, chips were going with lower and lower voltage. So, probably 25 years ago, 30 years ago, 5 volts was a standard. Now it's even less than 1 volt. Typical voltages can be 0.8, 0.6 volts. But of course, there's a limit, right? You cannot go to zero. You cannot get too close to zero, because then their high and low level would be indistinguishable, or there will be not enough safety margin to reliably tell whether we have zero voltage or non-zero voltage, right? Because that is tied to our Boolean values, true or false, right? So if you say false is 0 volts, true is the other level. If that other level is 5 volts, even if if the voltage fluctuates a little, you can still tell the difference between true and false. But if it's 0 and 0.1, right, the amount of fluctuation that you can afford is a lot less. So there's this natural limit to decreasing the voltage. Okay, and so that's an example of computing their power requirement. All right, so if we change their capacitive load, if we change the voltage and frequency, and we just compare, we see that there's this natural limit. We call it the power wall. We cannot reduce voltage further. We cannot dissipate more heat, because it is related to their physical size of the chip, okay, and their materials that are used to produce that chip. So how can we? What can we do? How can we improve performance? All right, we cannot lower the voltage anymore. We cannot increase frequencies anymore. So what do we do? Well, the natural answer is let's just go with more processors, right? Instead of uniprocessor, so a single processor, and here's the chart that shows their uniprocessor performance over time, and you can see that it was growing pretty fast for a good number of years, but then it kind of wears out. It kind of saturates, and so that is directly related to the Moore's law. One of you already mentioned, right? So Moore's law is no longer true, but it was it did hold for a good number of years, but not anymore. So the answer is we go with multiple processors, right, or multiple cores, and we are going to talk about it in the second half of the course. So basically, it means that we have multiple processors, more than one processor per chip, or multiple chips on the same motherboard, on the same within the same system. And the challenge is that it requires that we write our programs differently. So it requires explicitly parallel programming, and we will look into that in this course. But like I mentioned, if you really want to know more, not just a very high-level introduction in this course, but you want to go deeper into parallel programming, consider taking parallel programming course with Professor Carruthers. Right, there's a lot of different problems that need to be solved if you want to write an efficient parallel program. It is hard to do, but it's for that reason. It means that not that many people, relatively on the relative scale, of course, can know how to do it, and that's why it's a skill that is in high demand, right? So programmers who know how to do parallel programming, they are generally in high demand because it's hard and you need to understand a lot of different things to write efficient parallel programs. All right, and then finally, the benchmarks. This is related to their problem. How do we compare different architectures, different processors? Let's say for marketing purposes, or if we are trying to figure out which system we need to buy, we would like to have a way of measuring performance. So there are many different benchmarks available. One of them, one of their ways to do that is actually just look at their number of operations per second, and that MIPS abbreviation that we talked before, it's million instructions per second. Okay, so that's also a benchmark. It's pretty common. You can see, a similar metric called flops, floating operations per second, or mega flops, or gigaflops, or teraflops, whatever. And that's kind of similar conceptually to MIPS, just for not any instruction, but for floating point instructions. And both of those metrics, MIPS and flops, they are not, well, they're widely used. They're easy to compute. They're not exactly meaningful, especially when you're comparing different systems, because those metrics do not take into account the differences in architecture. So they're just comparing the number of instructions per second, or floating point operations per second, and nothing else. So take them with a grain of salt. Right, they're simple measures, but not necessarily the best. And benchmarks are usually more complicated. So SPEC is one of their most common most popular ones. It's a standard performance evaluation core. So it's a set of different tasks that are run on the machine, on the system being tested, and then the result is a number, and then those numbers can actually be used to compare different systems. Excuse me. Well, MIPS for the architecture is microprocessor without interlocked pipeline stages. Exactly. This is our MIPS architecture and MIPS assembly language. Exactly. But MIPS also stands, the same abbreviation stands for a total different things as million instructions per second. Right. So you can say this processor has a performance of 5 MIPS. All right. So this is one of their measures that make up SPEC, CPU 2006, and there's a bunch of others you can see in the description. Right. We have different tasks, and those are just their performance data for a particular Intel Xeon processor. Look at their SPEC ratio. This is one of the benchmarks, and as you can see, for different tasks, the same processor may have different values. And look at the CPI, right? So this is interesting. We see that on average, this particular processor, for most of their operations, it actually boasts less than the CPI of less than 1. How is that possible? It turns out it is possible because advanced processors can actually execute multiple instructions per clock cycle. It's complicated. It requires special design, but it is possible, and that's why CPI can be less than 1. And if a processor, can, and because of that, quite often the CPI is actually inverted and is represented as IPC, instructions per clock cycle. and it's just the inverse of CPI, but it's just in many cases a measure that is more convenient to work with, right? So if you have a CPI of 0.5, it's the same as IPC of 2.0. It just means that on average, there are 2 instructions executed per clock cycle. Why geometric mean rather than some other sort of mean? It's just one of the benchmarks. It is believed to be representative of common computing tasks, but it's not the only metric. So that's the short answer. And I don't really want to go into much detail because spec is not the only benchmark, and with any benchmark, you can only trust it so much because again, it is trying to set up a level playing field for all participants, for all processors potentially that you're testing. But because of that, it may ignore some particular features of a given processor that may actually give that processor a competitive edge in real tasks. So that's why benchmarks can only tell you so much, right? They're not the only metric that should be used to compare the performance. And there's also spec power benchmark, which characterizes the number of operations per watt of energy, and that's their example. And here is their this spec power values for the same Intel Xeon processor. And here we can make a couple interesting notes. So here, note the average power as a function of the load. And even when the processor is not doing anything at 0 load, the power is still 48 watts, which is a lot. And if you look at their max power consumption, close to 350 watts, 48 is a significant portion of that maximum power consumption. So, and you look at 0 load, 0% load to 10% load, their power consumption goes up more than twice, whereas their load only goes up 10%. So you can see that probably what the problem is. There, you cannot, you do not have a good correlation between the load and the power. In other words, even if you have nothing to compute, you would not be able to easily bring the power to 0. Well, you can power down your processor, but then the startup time would be significant, right? So you cannot do it quickly. The power is still consumed because you still have their CPU, you still have the clock that is generated, and that clock still has to, every clock cycle it charges and then discharges all their capacitive loads. And that's why even if your processor is executing nothing, only NOPs, empty operations, as long as the clock is supplied, you're never going to bring the power to 0. And then processors with advanced power modes, they can stop the clock, they can power down different components like memory, cache, this and that, and bring the power down. But it's slow. You cannot do this often, right? You cannot stop the clock and then 10 nanoseconds later fire up the clock again, because it raises their synchronization issues and all the other different kinds, different types of issues, including just pure electrical engineering issues. So you cannot do that quickly. Okay, and this is of course a big problem because if you think about and let me, there's a slide here. Yeah, so lower power at idle. Okay, if we look at that benchmark that we just saw, then you see that it is efficient to load your hardware close to 100%, right? So that you get most out of it, and because if you don't, you will still have to pay your electric bill, right? So the power consumption is still significant. The truth is, unfortunately, that for cloud computing, for data centers, it's not advisable to engineer those facilities for 100% load. Because if you operate normally under 100% load, it's efficient. But what if you need even more load? You cannot deliver it. And that's why like a data center is designed to operate at typically like 10 to 50% load, so that if there is a spike in demand, then there is this room that we can pump up the performance, right? So that we can go from 50% load to 100% load if there is a spike in demand. And that's why those facilities, they do not work at 100% load, pretty much never, less than 1% of the time, as the slide says. Okay, and that means that most of the time you are operating at a very low percentage of load, and that means that you're not power efficient, and that's that's a big challenge, because if we could design processors so that their that their power consumption is proportional to load, that would be a lot better, but it's a big engineering challenge. Okay, and so another thing that will actually be on our exam, and that is important to know, is Amdahl's law, and we'll talk more about this law when we cover when we talk about parallel programming in the second half of this course. But for now, it's important to grasp the basic concept and just this one formula. So we want to improve, an aspect of some computation, and we expect that the improvement in overall performance is going to be proportional. So, for example, imagine that you have your program, you run your program, it runs in 100 seconds. And then you say, well, but I can make, let's say, a particular function in my program run 2 times faster, but only that one function. How can you do that? Well, the most straightforward solution would be if that function can be easily parallelized, so run efficiently on multiple processors, that would be the way to go. So imagine those, that function computes just performs a bunch of multiplications that are independent of each other, and you can perform those multiplications in parallel on 2 processors. And then, of course, you would improve the runtime of this function by a factor of 2, right? 2 more, twice the number of processors will execute, will go through those multiplications twice as fast. Okay, and so their T affected would be their time of the function, or in general any piece of code that can be improved, and by how much improved is given by this improvement factor. T unaffected is the time that it takes for all other pieces of program, all other pieces of code that would not benefit from this improvement. For example, if you're performing an I/O, right, you are reading and writing files, it's not a CPU bound operation, right? If you use 10 times 10 CPUs to perform your I/O, it's not going to go any faster because it's not using CPU. CPU is not a bottleneck. The bottleneck is that single, let's say hard drive that you're reading from, right? Because there's only one. It doesn't matter how many processors you throw at the task. It's not gonna do it any good, and that's why we call such pieces of code unaffected. And here's an example of this Amdahl's law in action, and the overall kind of idea behind that formula is you can improve the runtime of your program, but it will, if only part of your code can benefit from some improvement, you will not see a proportional improvement in the overall runtime. So, for example, if you have here, you have a total runtime of 100 seconds, and multiplication takes 80 seconds. So that means this T unaffected is 20 seconds, right? So it means that even if your multiplication, right, can be parallelized, and you can improve it by a factor of 2, 4, 10, 100, 1 billion, your overall runtime is not going to be less than 20 seconds because this T unaffected, the 20 seconds, let's say that your IO takes, it's not going to see any improvement no matter how many processors you threw at this program, right? It's still going to be 20 seconds plus something, right? And that something can be, you can improve it, of course, and it can get very close to zero. So you can say, let's imagine it's effectively zero, but this 20 is not going anywhere. So there's no way you can make your program run in 20 seconds or less. And this is exactly what Amdahl's law captures. It is important to make sure that when you run your program, you have as few pieces that cannot be improved by throwing more hardware. Like this T unaffected has to be as little as possible. Because then this T affected would be a larger portion of your program that would benefit from this improvement. An example where it can be done, let's say your, let me see if I can actually right here, should be able to. All right, so let's say it's not 80, 100, but it's 90 and 100. So then this T unaffected is 10. And we want this part to be 10, okay? Is that making sense? And then, so our T unaffected was 90, right? So 90 seconds. So we had 90 seconds. We need to improve by a certain factor. We don't know which. And we want to get 10 seconds runtime. So what our improvement factor needs to be? It needs to be 9, right? Is that making sense? So if we had initially, our program runs in 100 seconds, and we know multiplications take 90 of those 100, of that 100, then if we run multiplications on 9 processors instead of 1, then multiplications will be taking just 10 seconds. And everything else like IO would still be 10. It's not going to change, but 10 plus 10 is going to be 20. Okay. See how by reducing the ratio between T unaffected and T affected, we were able um, to achieve the goal, right? But it means that we had to change the program, right? It means that we have to, probably improve our IO so that it is a smaller portion of our overall runtime. So T improved would be 20, exactly. So in this formula, T affected would be 90, T improvement factor would be 9, T unaffected would still be 10. So we have 10 plus 10 is 20. Okay, is that making sense? Yeah, and there will be an Amdahl's law practice problem in the practice set that is coming up later tonight. So please make sure you don't miss that problem. All right, here's a pop quiz, and it's this one. All right, so it's basically the Amdahl's law problem. So hopefully it's self-explanatory, and we already talked about this part. So yeah, we are just at the end of this chapter 1 slides. We are going over some fallacies and pitfalls. So we already talked about their power problem, and here using MIPS as a performance metric. So MIPS has millions of instructions per second. We already talked about it. It doesn't account for the differences in architectures and in instruction sets, and it just takes it doesn't take into account their CPI. So MIPS in particular, just instructions per second. Even if some instructions may take more clock cycles than others, this metric MIPS does not take it into account, and that's why it is simple, but it's not very precise. All right, and that's pretty much everything that we had to talk about in in our chapter 1. So cost performance is improving. We see that. And there are hierarchical level of abstraction in both hardware and software. That's how we battle complexity by going with abstraction. Instruction set architecture, that's a hardware software interface, and we're gonna talk about it, and we already started the conversation about it with our MIPS example. Execution time is a very strong performance measure, not the only one, but one of the most common ones. And power is a limiting factor, and it's a big engineering problem, primarily as far as electrical engineering is concerned when designing chips and boards. And our answer to that is, well, if we're hitting those limits, we just go with more processors. We throw more processors at the task, and that is parallelism, which requires that we change the way we write programs. Right? We cannot use the same program to run on a parallel machine that we use to run on a single processor. There are there are frameworks, there are languages that allow you to get very close, but still it requires some additional effort. All right. So that was that, and we are done with chapter 1. And let's go over parts of chapter 2 that we kind of missed. And one of the let me start with this thing, because it is definitely something that you will need to know for their exam. You know what? Let me actually let's save it for Tuesday. It's still going to be on the exam, but we can save it Tuesday, next lecture. Okay. So in terms of their coverage, we will cover on our exam 1 everything up to this slide 61. Okay, so to give you, and we covered most of their material already, but we will cover the remaining material on Tuesday. Okay, exam 3, I mean. Can we bring a calculator to the exam? No. Will we need one? No. You should be able to compute everything by hand. And for that, of course, you need to know certain shortcuts. Okay, so like you need to kind of know your powers of 2, and you need to be able to add 2 decimal numbers on using pen and paper. So what pages in the book have we covered up to slide 61? Please ask that question on the forum, and I will answer it. I need to check the actual book. Okay. All right. So no calculator, no problem. No, there will be. Well, yeah. There will be questions where you have to perform some computation, but their numbers will be such that you should be able to do that easily, using pen and paper. Exam 3 is only on chapter 2 slides. No, exam 3 will cover everything that was not included in exam 2. So, definitely exec and fork will be on exam 2. So there will be a question, actually, I can tell you right now, there will be a question on fork and exec on this upcoming exam. And of course, there is a question on that in the practice problems. And this question is actually question 9 from exam 2 practice problems. Well, no more zombies. No, that's hold on. No. Zombies, yeah. Zombies is from the same topic, so it may appear, of course. Okay, office hours still in person. Office hours are both in person and WebEx, at least my office hours. So you can stop by my office. You can connect through WebEx. Either way, join the queue. But one thing that I wanted to go over now is, and let me see what my TAs and mentors suggested based on their experience with the lab. So one thing that they told me many students had difficult time understanding the the concept was the labels in MIPS code. So let me talk about those. So labels are just, well, they are labels, right? They mark pieces of code. So labels are not functions. Okay, so you can label any, and I'm showing this load store example from lecture notes. So a label is just something that we tag a particular instruction with, and you can tag every instruction with a label. So it's not a function. You cannot call it directly. You can use label if you want to go to that address, to that instruction, and that's why, as we shall see shortly, you can use them to, kind of do, um, to call functions. But effectively, this is just a jump, and a jump can be to any label. So it's up to you to, kind of see whether a label is callable as a function, or if we can jump to that label calling a function, or what would be an equivalent for a function in MIPS, or it's just a label that can be a target for their any branch operation. So main is this global name. That's how the simulator knows what where your program starts, and that's why in this text segment we declare that main is a global label. Right, so and you can use a different name, it doesn't really matter. And so hopefully you went through this in the lab, that we can see in MIPS every segment, every memory segment has to be specified explicitly. Like we have a data segment here, we have our text segment here, and it actually continues because we have code below, so it's that text/code segment. And then we will see shortly that stack segment we also have to to handle ourselves. It's no longer going to be handled for us, as was the case with C code. And even later we will look at the dynamic memory allocation. Okay, so with main, so this is the connection main here and main here. We declare main as the global label, and then whenever we need to, to branch, and so there's no example here, but let's see, we have an if-else example here, where we have this branch instruction with a label, exit. So exit is a label. You see, exit, we are just tagging this instruction as exit. And the thing is, if we branch, if this branch leads to this exit label, then execution continues here with this instruction, and then it just continues with the next instruction, and so forth. So you can see that exit is not a function at all. It's just a label where we can transfer control, where we can tell our program to continue execution from the instruction that is labeled with that label. All right. Yeah, dynamic location in MIPS is fun. It's actually not as bad as you might think. Procedures and functions in MIPS is a lot harder than actually doing dynamic allocation. Then dynamic allocation is going to be, just a syscall. Okay, and yeah, for syscalls, we didn't talk about them in the lecture, but hopefully they are pretty straightforward. You were supposed to get exposure to that in labs, and so it's very straightforward. Just put the right values in the. Yes, someone is asking a question. Okay. Yeah, JA is jump to address, exactly. And usually you want this with L, JAL. So this is jump address with linking, so that their address to which then to return from their function that you call, from the procedure that you call, is stored in this special RA register. We're going to talk about that next lecture on Tuesday. So someone asked another question that I thought was important. Can you explain more about their immediate, what immediate means? Sure. So immediate just means it's a constant. So here, li load immediate. We load immediate value. Immediate is just a fancy name for a constant. Load this constant one into this register. As I think I mentioned already, so load immediate is really not not an instruction; it's a pseudo instruction. But in any case, we can have add this command with all three registers, so no immediate values, and that's why we have just add. If we wanted to add with an to add the contents of a register with an immediate value, we would replace this last argument with our constant, like 5, 7, -2, and then use I instead of nothing here. So we would go with add I, and I think we had some examples here with add I. Definitely in the slides, but let me see if we have. I don't see anything here, and I don't want to go in the factorial, but in the slides that we covered last time, okay, so here's an example, right? So add I because you're not adding two registers and storing the result in the third register. You're adding the contents of a register with in a constant and storing it in the register. That's why you have add I. Yeah, there's no sub I. And in fact, you don't really need sub because you can always do add I with a negative constant. Okay, like this example shows. Okay, so we are at our time mark, 1:51, even 1 minute over. Yeah, please ask more questions on the Submiti forum during office hours. Please come to office hours. I'm always happy to see you folks. And thank you everyone for attending this lecture. And enjoy your weekend. Yeah, and TGIF. Have a good one, folks. TGIF. Sorry, what I'm talking about. TGIF. Yeah. All right.